In this video, I want to talk briefly about the Hausman test, which is a test of essentially whether we should be using random effects estimation or fixed effects estimation. So in order to talk about this test, we're going to talk about a particular example. So in this example, we have a dependent variable y, which depends on an individual's characteristics where the individual is given by I and for a particular point in time. And we say that this y is equal to beta 0 plus beta 1 times some explanatory variable which varies across individual and across time. And we also suppose that there is some sort of hidden unobserved factor alpha I, which we also should be including in our model. Even if we don't explicitly include it in our estimation strategy, this alpha I is always going to be there. Okay, so remember that random effects essentially assumes that the covariance of alpha I with the independent variable xit is equal to 0. And if this covariance is equal to 0, it is the case that both random effects and fixed effects are consistent estimators. And in the circumstance where this particular condition is satisfied, then not only do we know that random effects and fixed effects are both consistent, it is the case that random effects is more efficient than fixed effects. So the standard error of random effects should be less than the standard error of that which we would obtain via fixed effects. Okay, so now that we know these two particular things, we are almost in position to set up our particular test statistic. The final thing we need to note that is that if this above assumption isn't true, then it is not the case that random effects and fixed effects are consistent. If this above assumption isn't true, then fixed effects is solely consistent. And by writing solely here, I mean that random effects is no longer consistent. Okay, so on the basis of these three statements, we're able to start talking about the Hausman statistic. And the Hausman statistic for one particular explanatory factor is essentially constructed by the numerator is equal to the fixed effects estimated value of the parameter beta, or in this example beta 1, and I've put a star here to indicate that this is the actual value which is outputted from that estimation rather than the estimator, which is a function. And we take off the value which random effects outputs from that particular estimation strategy. And then we square the difference between these two estimation strategies or these two particular estimated parameters via the two different estimated strategies rather. And we divide it through by the variance of the fixed effects estimate minus the variance of the random effects estimate. And it turns out, under the null hypothesis being true, and I haven't defined what the null hypothesis is yet, but bear with me, then this is chi-squared with 1 degree of freedom. So what is the null hypothesis here? Well, the null hypothesis which we are testing against here is that the covariance of alpha I with xit is equal to 0. In other words, we're testing our null hypothesis here is that we should be able to use random effects. And the alternative is just that h0 isn't true. Okay, so what's the intuition behind this particular test statistic? Well, the way in which it works is that if the null hypothesis is true, then we know that these two particular statements are true. So we know that both random effects and fixed effects are consistent as a starting point. And if they're both consistent, then the difference between these two estimates, which is kind of what this numerator is, should be very, very small. Secondly, if this null hypothesis is true, then we know that the variance of fixed effects is greater than the variance of random effects. So whereas this numerator will be quite small, this denominator will be relatively large because there should be quite a big difference between the variance of fixed effects with that of random effects, which will mean that the value of W which we'll get out from this statistic will be quite small. And to see how this is important when we're saying under H0 this test statistic is chi-squared with 1 degree of freedom, we need to actually draw what a chi-squared statistic looks like with 1 degree of freedom, or a chi-squared distribution rather, with 1 degree of freedom. So the y-axis here is the probability and the x-axis here is the value of W. And for a chi-squared distribution with 1 degree of freedom, it looks something like this. So the overwhelming majority of values of W should be very, very close to 0. So if it actually turns out that W is close to 0, so perhaps we get a value of W which is something like this, then it is essentially quite likely that we would have got this value of W if the null hypothesis was true, because this is the distribution under the null hypothesis being true. Whereas if the null hypothesis is false, then essentially we're saying that the covariance of alpha I with xit does not equal 0. And if that is the case, then it is this third statement which is going to come into play. And the way in which it works is that if this third statement is true, then the numerator now is going to be relatively large, because there is going to be some difference between the point estimates of fixed effects versus random effects. Because fixed effects is the only one which is consistent, so random effects is most likely going to be quite different to that. And because of this large numerator, the value of W, the Hausman statistic which we get, could be quite a long way away from 0, so perhaps it's somewhere like this. And it is actually quite unlikely, rather, that we would get a value of W which is this far away from 0 if the null hypothesis was true. So if we get a large value of W, we are going to reject the null hypothesis, and it looks likely that fixed effects estimation is the way to go, because essentially we have some covariance between alpha I and xit which doesn't equal 0. So just to summarise, if we conduct this test and we do not reject the null hypothesis, then we conclude that random effects and fixed effects are both consistent, but we should use random effects because of the fact that its variance is lower than that of fixed effects. Whereas if we reject the null hypothesis, then we are going to conclude that fixed effects is the estimation strategy to go with, because of the fact that only fixed effects estimation is consistent in this circumstance. Essentially, what this particular statistic W is doing is it is comparing the consistency of the two estimators, which is the numerator, with the relative gains of efficiency which can be obtained by using random effects over fixed effects.